Okay, so in a system at equilibrium, the rate of the forward change and the rate of the reverse change are equal. But what does that tell you about how much reactants and products you have at equilibrium? I'll tell you how much. Nothing. You have no idea how much reactant and product there is at equilibrium. If a reaction went to completion, you'd have no reactants and all products. If a reaction didn't even get started, you'd have all reactants and no products. But what about equilibrium? How far does a reaction get before reaching equilibrium? How far a reaction gets can be measured using KEQ, the equilibrium constant. The equilibrium constant can be calculated by setting up what's called the mass action expression. The mass action expression is basically the concentration of the products divided by the concentration of the reactants. If there are any coefficients in the balanced reaction, they become exponents. And the plus signs become multiplied signs when you write the mass action expression. So, to do that, let me show you a few examples. And I know we're at equilibrium and both reactions are happening, but the left side is still designated as reactants and the right side is still designated as products. KEQ is equal to the concentration of products divided by the concentration of the reactants. So our products will go on top and our reactants will go on the bottom. Now, coefficients become exponents. So 2CO becomes CO squared. And I used brackets instead of parentheses because brackets represent molar concentration, the molarity in moles per liter. And O2, now it says here any plus signs like that becomes multiply signs. Multiplied by O2. Now since oxygen doesn't have a coefficient, we don't put an exponent. Over the reactants, which is CO2, and squared, because a coefficient becomes the exponent. And that's how you would set up the KEQ, and then this would equal KEQ. And then what would happen is you'd be given the concentrations, you'd plug them into this formula, and you would get the KEQ's value. Let's set this one up. Again, the stuff on the right is the products. So H2, no coefficient, so we don't put an exponent. Plus sign becomes a times sign. I2, again, no coefficient, so no exponent. So those are the products over the reactants. HI, hi! And since there's a coefficient of 2, the exponent is 2. And again, you'd be given the numbers and you could plug them in and solve for this mass action expression, and that would give you the value for the equilibrium constant, a number which tells you how far the reaction goes before you reach equilibrium. For a solution equilibrium, same thing. KEQ is equal to, the products are these things here, so H plus 1 squared. The charge is here, so I need to make sure it's there inside the brackets, times SO4 minus 2. That's the charge of the sulfate ion, so I include it inside the brackets, over H2SO4. And that would be the equilibrium constant for that equilibrium. Now, to solve for KEQ, what we do is we set up the mass action expression, and then we plug in the numbers. So, KEQ equals, well, here are our products, CO squared, plus becomes times O2 over CO2 squared. Then all you have to do is just plug in the numbers and solve. So if CO2 is 4.0 molar, that means we've got 4.0 on the bottom, and we have to square it, because that's what our mass action expression tells us we have to do. The CO is 2.0 molar, and again we're going to square it, because that's what our mass action expression tells us to do, times.
Do you do everything the mass action expression tells you to do? What if it told you it was going to jump off a bridge? Would you follow it?
Well, in this case, yeah, you would. Okay, so O2's concentration is 1.0 molar. And because there's no exponent, we wouldn't do anything to that. All right, so let's see. What does this come out to? 2 squared is 4. 4 times 1 is 4. 4 squared is 16. 2 sig figs, 2 sig figs, 2 sig figs, 2 sig figs, 2 sig figs. What's 4 divided by 16? 0.25. And that's the value for KEQ. Now, that's great, but what does that value mean? Okay, so you've set up the mass action expression, you've plugged in the numbers, and you've gotten an answer. Great, now what? Here's how to use KEQ to determine how far a reaction gets before reaching equilibrium. First, if KEQ equals 0, that means the reaction doesn't start at all. It's a non-spontaneous reaction. You got all reactants and no products. As KEQ increases, the more products get made. Why? Because KEQ equals products over reactants. So the greater our final number, the greater our numerator and the smaller our denominator. As we get more products, our value increases. If we have less products, our value decreases. So the greater the value of KEQ, the further the reaction went before reaching equilibrium. When the concentrations are equal, you'll get a KEQ of 1, and that means it went halfway before reaching equilibrium. This value here means that the reaction went less than halfway before reaching equilibrium. So if KEQ is smaller than 1, the reaction didn't go very far. You still have a lot more reactants than products. If KEQ is greater than 1, that means that the reaction went a lot further. There are more products than reactants. And if KEQ equals infinity, what that means is this. Imagine if you had 100% products and 0% reactants. You're doing 100 divided by 0. What happens when you divide a number by 0? It becomes undefined. Now what does that mean exactly? Well, as the numerator gets larger and larger and the denominator gets smaller and smaller towards 0, the number gets bigger and bigger and bigger. And as the denominator gets smaller and approaches 0, our answer approaches infinity. A number so huge that there's no name for it. We just have to call it infinity because it's infinitely huge. There are days that I feel like that. Hey, no fat jokes. If KEQ is infinity, which would show up as large or very large, then the reaction went all the way to completion without reaching equilibrium at all. So 0 didn't start. As KEQ gets higher, it goes further towards completion until, bam, if KEQ is infinity, then it goes all the way to completion. Reactants completely turn into products without reaching equilibrium at any point. This is what happens if both factors are unfavored, delta H and delta S. If they're both unfavored, that's what's going to happen. If they're both favored, that's what's going to happen. If one's favored and the other is unfavored, that's what's going to happen. It's going to stop at some point. Now, equilibrium point depends on temperature. So, which reaction went the furthest towards completion? Well, the furthest towards completion would be the highest KEQ. Which of these 4 values is the largest? Well, is it 10 to the negative 5th or 10 to the 4th? 2 times 10 to the 4th would be 2. 1, 2, 3, 4. That would be it, 20,000. 4 times 10 to the negative 5th would be that. So it's easy to see that that is by far the bigger number, and that's the smallest. So which one goes least towards completion? That would be the smallest value. So largest value, furthest to completion. Smallest value, least far towards completion. Now, KEQ goes a lot deeper than this, and there are a lot of different equilibrium constants that are all based off of KEQ, but they are beyond the scope of this accelerated enriched chemistry class.